Let's look into solving second order ordinary differential equations with non-constant coefficients. These are linear differential equations, but since the coefficients are functions of x, you cannot use the traditional methods such as Lagrange's method or Euler-Ansatz. The Bernoulli method must be used instead. It's a very general method, and we will use it to get some important insights about equations like Bessel's equation, which falls under this category. Many other differential equations like Legendre's equations and Hermite equation, they all fall under the same category. So the Bernoulli method will prove to be a good first way to attack it. It doesn't solve the problem, but it gives us a good way to make a dent in it. So the method consists in writing the function y as a product of two functions, u and v. Now, at first blush, it might seem like a crazy thing to do, but you can see the kinship with the Lagrange ansatz. Lagrange ansatz also has us think of the coefficient c1 and c2 as being functions of x times the solution to the homogeneous equation. However, this is an homogeneous differential equation, so the kinship ends there. If you do this, the first derivative is u prime v plus uv prime, and the second derivative is u double prime v plus 2u prime v prime plus uv double prime. So the original ordinary differential equation that we have under this condition becomes the following: u double prime, and I divide both sides by v, so I end up getting 2v prime over v plus p1 u prime plus v double prime plus p1v prime plus p2v. Now I have taken the position that somehow u is more important than v. That is, of course, completely arbitrary, and it's entirely because u comes before v in the alphabet that I did this. You could have as well made v your hero and put u in the parentheses. Well, whatever it is, we're going to call this function q tilde of x. It has to be a function of x, so that's a good way of talking about it. Now there are two possibilities. The first possibility is that by hook or crook, you've managed to find one solution. Oftentimes the solution is found by guessing or just trying out a bunch of stuff, and you'll find one, bang, it satisfies the ODE. So when you get lucky like that, you say that v of x is a known solution. Let's suppose it's known. Then what we're going to do, if v of x is a known solution, by the way, then this coefficient is 0, because v of x satisfies the original differential equation. So this coefficient becomes 0. And now we have a very simple differential equation, u double prime plus qu prime equal to 0. And now we can reduce the order of this equation by setting w equals u prime, and then we're going to get w prime plus qw equals 0. It's very easy to solve this by separation of variables. We'll do that by doing dw by w equals negative q dx. Integrate both sides, and I get w equals some constant c times e to the minus integral q dx. So we have solved this equation, but be careful, w is u prime, so we still have to solve for u. So that gives me u equals some constant c times the integral of e to the minus integral q dx plus c. Another constant, so let's call it c1. This may all be very difficult to do, but there are computers for that very reason. So y equals cv, because y is the product of u and v, so it's going to be cv times that integral e to the minus integral q dx plus c1v. And that's a full solution. So we have solved this problem completely. If you're able to guess the first solution, then the full solution is found as follows. Now suppose you don't know anything and you try guessing solutions and they all land flat. Then what do you do? Now what we can do is, there is enough freedom built into this method, the Bernoulli method, known as a gauge freedom. And so we can use the gauge freedom, because after all, when you say a function is a product of two functions, you can actually impose an additional condition known as a gauge condition. And that gauge freedom is that you can demand that even if you don't know what v is, it should satisfy this equation. So what I'm going to do is I'm going to demand that 2v over v prime plus p1 equals 0. Well, that's pretty easy to solve. That gives me dv upon v equals negative 1/2 p1 dx. And I integrate both sides, and I end up getting e to the v equals e to the minus 1/2 integral p1 dx. So I know, so once I have that, then I just have u double prime plus q tilde of u equals 0. Well, that looks a lot like simple harmonic oscillation, except q is not constant, so that cannot be simple harmonic motion either. But maybe as x goes to infinity, it could look like simple harmonic motion. So at least we can get some asymptotics out of this. Once you have the asymptotic u, you can multiply it by the v to get the full solution at infinity. So these are the very general methods called Bernoulli technique, and let's try to apply it to reduce a very famous equation in mathematical physics called the Bessel's equation. The Bessel equation will form a big part of future videos, but it's good to have a little peek at Bessel's equation in a very general setting before we go into the specifics of solving it using the method of Frobenius series. The series method is eventually going to be the method that's useful for all conditions where you don't have any luxury of these methods. But even if you are going to be solving the problem using series, it's good to get a feel of what's going on using the Bernoulli technique. So I would like to encourage you to read the notes corresponding to this from my course website. It's example 9. But roughly speaking, what we're going to do is we're going to follow the Bernoulli method. So I'll divide both sides by x squared first. So I'm going to get y double prime plus 1 over x y prime plus 1 minus nu squared over x squared y equal to 0. Nu, by the way, is called the order of the Bessel equation. So as written, our functions, you have to bring it to this form because you have to identify p1 like that, and that's going to be your p2 function. And you do this and since p1 equals 1 over x, you can put this immediately using the gauge freedom because you don't know anything about the Bessel equation. So rather than guessing a solution, we can immediately use the gauge freedom that we have here, and here, and find out what v is. So this tells me that v equals e to the minus, let me just follow the prescription to the letter, integral dx over x. Well, dx over x, when you integrate, you get natural log. So that's e to the minus 1/2 natural log of x. However, Negative 1/2 can go inside the natural log, and I get e to the natural log of x to the minus 1/2. Now e and natural log are natural enemies, so I get x to the minus half as your v function. Now the ordinary differential equation just becomes u double prime plus q tilde u equals 0, and q tilde is all this stuff here. It's v double prime plus p1 v prime plus p2 v over v times u equals 0. Now I'll let you read the notes for this, but you'll end up getting the following. You'll end up getting u double prime plus 1 minus nu squared minus 1/4 over x squared u. Now that's a very beautiful ordinary differential equation, because right now you know nothing about the Bernoulli equation. You did not even have to know that it was called the Bessel equation. And I just gave you the name. It could just be a name. So this is just a named equation, and you come to this point by just stumbling around with Bernoulli method. And what do you find? You find this incredible finding that if nu were equal to plus or minus half, then you get the simple harmonic equation, u double prime plus u equals 0. And that solution to that is very elementary. It's u equals the linear combination of cosine of x plus sine of x. Well, but recall that u is just one small part of the whole story, and the full solution is u times v. So this gives us the exact solution for nu equals plus or minus half. You're going to get v is x to the minus half, by the way. So you're going to get a cosine x over root x plus b sine x over root x. These are known as the j plus and j minus. Where j is the Bessel function. So we have somehow stumbled into the first solution for Bessel's equation. Now if nu is not equal to plus or minus half, then you're out of luck. Suppose, for example, nu is 3, then this part will not be 0. But what you do see is that you have a 1 over x squared. As x goes to infinity, that should look like a simple harmonic oscillation. So we are led to conclude that all orders of Bessel's equation have j plus or minus half asymptotes. So asymptotically, they all look like j plus or minus. And so that's a very useful thing to know. They basically look like sine and cosines, but killed by 1 over root x, which means that the oscillations are damped. So you understand quite a bit about even a complicated equation like Bessel's equation. Now, of course, to get any further, to get the actual behavior of Bessel's equation, not at infinity, but at finite values where most engineering applications occur, you have to do something else. And that would be the method of Frobenius that we'll be dealing with a lot in future videos.